So start recording. So, any questions you particularly want me to go through looking at this right now? There is also one on the back page, on the back side as well. If not, we'll just start at the top. Which one? The last one. Okay, so we'll start with 2016 11G. So let me just find that one. Oh yeah. This one. All right. So we are solving this trig equation and it equals a half, right? And as opposed to what we're doing in year 11, where we set it from 0 to 360, now we're doing 0 to 2 pi. Okay, so this is a trig equation. So when we're solving trig equations, generally the first thing we want to do is we want to think about, well, actually, the point of what we're trying to do here is look at the marks and then try to determine where the marks are going to be allocated. Okay, so this is 2 marks. Where do we think the marks are going to be before we start jumping into it? One of them would be obviously the solution, right? But the other thing is we've got x over 2. So you might remember when there's x over 2, that little modifier, there's something that we're going to do at the end. So we'll get to it when we go through the solution, but that's going to be the 2 marks, I'd say. So there'll be 1 mark for just finding, like, if it just said sine x equals 1 over 2, you'd find some solutions. But then saying that this is sine x over 2 equals 1 over 2, that's going to change our answers just slightly. So let's see how this goes. So to start us off, we have sine something equals positive 1 over 2. So first thing, which quadrants are we looking at? Yeah, the first and second. So we'll write that down. So first and second, because of our ASTC. So now that we've done that, we know it's in the first and second. So no matter what quadrant we find the answer in, we always want to find the first quadrant answer, and to change that to one of our solutions. Okay. So sine what? So in the first quadrant, sine what equals 1 over 2. Sine 30, but radians. So sine pi over 6. I mean, if you did do this whole question saying sine 30 and then sine 150, which is what we're going to get in a second, and then at the very end of your answer, then change it into radians, that would be totally fine. Alright? So if you're more comfortable solving and working with degrees and change at the end, totally fine. But you do need to change it, okay? Because it is saying between 0 and 2 pi. It's not saying between 0 and 2 pi degrees. Because 2 pi degrees is like what? Just a little bit more than 6 degrees. Okay, because 2 times pi. Alright, so we've got to make sure that we're thinking radians. And then so in the second quad, now that we know what the first quadrant answer is, remember what we go in that second quad, we do 180 minus that first quad answer. Okay, so 180 degrees minus 30 degrees is 150 degrees, and then we want to change the 150 degrees into radians. So what would that be? So if 30 degrees is pi over 6, how many lots of 30 degrees is in 150? 5, so it would be 5 pi over 6. And again, what you could do as well is you could, again, if you got 150, do 150 over 180, which is 5 over 6, and then chuck a pi in. That's the other way of doing it. And that also equals 1 over 2. Alright, so we have our 2 solutions so far, but those 2 aren't going to be the answer. We'll get to y in a second. So what we've done is we found the 2 solutions, the 2 positive solutions in those quadrants. So therefore we'll say x over 2 equals pi over 6 and 5 pi over 6. And that's good enough for 1 mark. Okay? Thing is though, what's the last thing I'm going to do here? pun? Yeah, we need to find x, right? Because what we found here is we found x over 2. So if that just said sine x, then yeah, we found the answers. But now this is saying x over 2, so I'm also going to need to then do one last thing at the end to get rid of that 2. So how am I going to get rid of that 2? Multiply. So that means x is going to be 2 pi over 6, which is pi over 3. Yeah, I'll just write it as 2 pi over 6 first, and 10 pi over 6, which also, if we simplify it, pi over 3 and 5 pi over 3. And there you go, there's the full mark. So that's your second low mark. So I'd probably say definitely it's 1 mark for getting up to there, and perhaps it's 1 mark to get to there. So yeah. And if we again wanted to think about these in degrees, remember that this is 30 degrees and this is 150 degrees. So when I times it by 2, that's 60 degrees, which is pi over 3, and that's 300 degrees. So if you do 300 over 180, that's 5 over 3, which I'm applying. Okay? So if you went through this whole question in degrees, in degrees, in degrees, and then the very last line said, oh, and that's pi over 3 and 5 pi over 3, totally fine. Okay, as long as you end up in radians. That's cool. I would say if you ended up your answer as x, if you left this as your answer, you might get 1 mark. You might not even get a mark, because not only have you not multiplied by 2, or maybe if you just wrote it as that, because not only have you multiplied it by 2, you not multiplied it by 2, but you also haven't changed it into radians. Okay, so just be wary of that. Basically, I don't think I've seen a HSC question with trig equations in which it wasn't asking it for radians, so you don't need to worry too much about it, just remember to do it in radians, but then also look for those little modifiers at the end of the question. Anyway, do you want me to quickly run through that one again? Yeah, I mean, basically it's like positive first and second, found the 2 answers, but realized it's x over 2, so I just have to multiply it by 2. Cool. Do you want to choose the next one, or should I choose? Or I think that's supposed to say 2011 question 4B, by the way, not 2001. Definitely supposed to be saying that. But yeah. Alright, well I'm going to choose the one on the back side, 2010 question 3B. And in fact, I'm just going to do another slide. So, this is 2010 question 3B. And so, it just starts us off by saying, sketch the curve y equals x. Okay? Now, you guys might know what that looks like. What does that kind of look like? Yeah, so the exponential means it never touches the x-axis, so it goes up like that. So the ln x goes up like that, so it never touches the y-axis. So if you were to do a very quick sketch, it just looks. So what's its x-intercept? Well, what's the y-intercept in exponential functions? No, the y-intercept. So it goes through 1. So for this ln function, it's just that. That's good enough for a mark. Okay? Because maybe I should do an axis bit as well. Because it never touches the x-axis. So you might remember that the y equals e to the power of x just looks like that. Okay? And as we know, logarithms and exponentials are basically opposites of each other. Alright? So we have a basic function like that. And that's your 1 mark. If you didn't know what the shape looks like, how could you sketch this function? Table of values. Okay? Remember, if you ever get stuck, just do a table of values. And if you just picked a few things, like if I did x equals -1, like if I do ln -1, it's going to give me math error. If I do ln 0, it's going to give me a math error, but that's not in the domain. If I did x equals 1, it'll give me 0. If I did x equals 2, it'll give me whatever ln 2 is. And then you can just plug a few values, and maybe if I did ln half, it'll give me like negative something point or other. But you'll be able to, after putting a few values, you start to see the shape happening, and then you're like, oh, okay, it kind of looks like this, and yeah, it does. Okay, so that's fine. Right, that's enough for that mark. So now we want to use trap rule with 3 function values to find an approximation to that. Now we need to find an approximation to that because we can't actually integrate ln x. Right, we've never talked about or never learned how to find ln x. It's very hard to do. We know something that if we integrate it becomes ln x, like if you integrate 1 over x, it becomes ln x. We've never actually integrated ln x. So we need to use one of these approximation methods. So if you wondered, well, why do we need to know Simpson's rule and trapezoidal rule? This is kind of one of those instances where integrating itself is a pain in the butt, but we can get something close to it. So trapezoidal rule with 3 function values. What does 3 function values mean? How many applications? Not 1. That's Simpson's rule. Alright, so it's going to be 2. What we're essentially doing here, if I were to split this up, and looking at your graph that you just drew, so we're doing it between 3 and 1. So that means our first function value is going to be at 1. Here's 3. And we need a third function value, which is at 2. And remember that trapezoidal rule is based on drawing a couple of trapeziums underneath the curve. Okay? So basically we're doing this. And then we're doing this, and we're finding the area in both of those. So those 3 function values create 2 trapeziums next to each other. So this is 2 applications. So now that we've got that, one application in trapezoidal rule, if we just write the formula, it's the area is approximately equal to, let me just remind myself what it is. It's b minus a over 2 f a plus f b. Yeah. I mean, that's on the formula sheet. But basically what we're saying here is, for each application, we find the distance between the 2 function values. So here we find the distance between 1 and 2, which is obviously 1. Okay? And then we're finding the y coordinate at 1, finding the y coordinate at 2. Okay? And then we add them. So, because to remember where that's based from, the area of a trapezium is given by the formula half times the height times a plus b. Alright? This time the height is the distance between the 2 x values. So h is b minus a. And the height, this a plus b, so if I'm looking at this, that's a, that's b. So it's the y value of the first point plus the y value of the second point. So that's where trapezoidal rule comes from. Just a quick recap on that. So we're going to do this twice. So hey, you can either do it with one big line, or you could kind of do it, I'm going to call it the way that I kind of like to do it. I'll say that A1 is approximately equal to, so I'm doing this first one is from 1 to 2. Alright? So 2 minus 1 is 1, and 2. And then so when I do ln 1, it equals 0. And when I do ln 2, I'm just going to leave it as ln 2. So the first area, that first trapezium, the area of that is going to be ln 2 over 2. Yeah? Because it's half. Yeah, so 0 plus ln 2 is just ln 2. That's half. And then, so my next application is from 2 to 3. So let's call that A2. And so the difference between 3 and 2 is again 1. And that's just ln 2 plus ln 3, which equals ln 2 plus ln 3 over 2. And if I wanted to be fancy, how can I write that in terms of just 1 ln? What's ln 2 plus ln 3? And then when you're adding 2, you multiply them. So that'll be ln 6 over 2. So what we're saying here is the area of this red trapezium, which is actually a triangle here, is ln 2 over 2. And the area of that green trapezium there is ln 6 over 2. So therefore, the approximate area of that bit, therefore area equals ln 2 over 2 plus ln 6 over 2, which we could also write as ln 2 plus ln 6 over 2, which we could also do ln 12 over 2. Yeah? Now you could have just left it as that, or that, or that. Basically you needed to add those two answers. Alright. And lastly, state whether the approximation found in blah 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 is going to be less or greater than. Now what you can't do is actually integrate it and just compare your two answers, because like I said, we haven't learned how to integrate things. So this is kind of like one of those questions where there's no real calculations and math involved here. It's more just understanding the theory or the idea behind trapezoidal. So going back here for a second, in my sketch, are those trapeziums above or below the curve? Below. Because there's kind of like a bit of a gap. Like if the curve is kind of going like that, and trapezoidal rule is based on having like flat tops, okay? So from that area that we just found, is it going to be greater than or less than the actual area bound underneath the curve? It's going to be less than. It's going to be just a tiny little bit less than, but like we see that this black area here, and that very small black area there, they haven't been accounted for. Alright? So we're kind of, this approximation is kind of like, yeah, it's almost accurate, but there's like a little bit that we can't find. And that little bit is more in here. So an example of when trapezoidal rule isn't always going to be less than. Like let's say the curve was like that, and there was my function value, there was my function value, there was my function value. You see that the flat tops go over it. So in this case, trapezoidal rule will be larger. Okay, so it really depends on the concavity of the curve at that point as well. Alright? So I guess we need to say the approximation is less than the exact value, less than the exact value or the exact area, because the trapeziums are beneath the curve. Just something along those lines. Like you just need to basically explain what you're saying. And in this case, we see that the trapeziums are below the curve. Say that. Okay. So yeah, there's no real calculations there. It's more of a justified answer. And there's generally like one or two of those questions in all these tests. They generally throw them in. It generally be like at the one mark at the end of the question, like what you see here. It's kind of like that. Explain what you're saying. Any other questions that immediately jump out to you? 4B, 2011. 4B, sure. This is it, right? Yeah. So we want to evaluate this. Now it looks like quite ugly, but in fact, if you just kind of look at it for a second, like, oh, actually, I mean, it looks ugly because you've got e to the power 3 and e as your boundary points and 5 over x, and it kind of looks like it's all over the place, but it's not too bad. So immediately when you're integrating a big fraction, it's not a big fraction, but you're integrating a fraction, what should we immediately be thinking of? Not getting x by itself. Pardon? Not even put the x on top, because if I did that, I mean, this would equal e to the power 3 5 x to the power negative 1 ds. That is true. But yeah, but then when you integrate that, problem is, how do you integrate just normal functions? Well, you would increase negative 1 by 1, so you've got 0, x to the power 0, and then you divide by the new power, and you divide by 0 rho. Okay, there's our problem. Alright, we're not allowed to divide by 0, so we can't do that. This is one of those instances where we want to make the numerator be the derivative of the denominator. Because remember that whole thing where if I'm integrating, if I've got f dash x and fx, like if my numerator is a derivative of the denominator, that equals ln of fx. Alright? So this is going back to that whole goal idea. What's our goal? No, what's the derivative of the bottom? 1. So my goal is 1. I can either make the bottom be 5x, so that means I change my goal to be 5x, to be 5, or I can change the numerator to be 1. Yeah, you can multiply by 1 over 5 over 1 over 5, or we could multiply top and bottom by 5. So go from here. We've got e to the power 3 e 5 over 5 times 5 over x dx. Okay. So by multiplying by 5 over 5, I'm just multiplying by 1. I'm not really changing it. Alright? And then so, what do I want to move over? Do I move the top or the bottom? I want to move the bottom. If I move the top, I'm going to get further away. Because then I'll be saying now my top is 25 and I want it to be 1. So I have e3 e 5 over 1 times 5 over 5x dx. And now what can I do with that 5 over 1? Yeah, I'll bring it out the front. So what I'll get is 5, and then what's the integral of that? Then 5x, right? We could also at this point also cancel out the 5s and then just be ln x. It doesn't matter though, okay? You might be thinking, well, of course it matters. I mean, there's a difference between ln x and ln 5x, and generally you're right. But because we're doing this, when we sub in the numbers, it's actually all going to sort itself out at the end of the day. So whether you write in here ln 5x, and I'm just going to do that just for the sake of that's what we just did. But if you were to do this whole question writing ln x here, you'd get the same thing. And then so now what we do is we're going to so what we'll do now is do the whole substitution thing. So we have 5 times, and we're just keeping that 5 out the front. So this would be ln 5e cubed minus ln 5e. It's kind of ugly because I've kept the 5s. But, I mean, what we could just do from here, I could rewrite this as 5 ln, or I could write this, well, what can I do with that power of 3? To bring out the front, so I've got 3 ln 5e minus ln 5e. Well, I mean, 3 ln 5e minus ln 5e is 2 ln 5e, right? Okay, because if you kind of think of ln 5e as x, so 3x minus x, 2x. And then if I'm timesing by 5, of 10 ln 5e. So if I ask you what's 3x minus x, you'd say 2x, right? Alright, and then I just did that 2 times 5, which is 10. Alright? So instead of x, I've got ln 5e, but they're still like terms. Alright, at the end of the day they are like terms. So 5 ln 5e minus ln 5e is 2 ln 5e. 5 times 2 ln 5e is 10. There you go. Yeah. In this one, we don't integrate. We can't. Oh. No, because when I ask you to do Simpson's rule, trapezoidal rule, it's specifically asking you to do that for a reason. It's like, if you were to, like, if the question was just like, I mean, it probably wouldn't ask you that in the first place. It would, generally, if it's a Simpsons or trapezoidal rule, they'll give you something that you can't integrate anyway. If I asked you to do that, for instance, so x is the integral of x, which is 1 over 2x squared. This is how I divide by new now. Yeah. Even though I can integrate that very easily, if it asks me to do Simpson's rule, trapezoidal rule, or whatever, I have to do them. Okay. But in that particular case, when we had ln x, we don't know how to integrate ln x, so it wasn't too much of an issue. Any last minute questions before we head off? Let's do 2015 12A, just real quick. Alright. Oh, this is like actually incredibly similar to the question we did right at the start. Alright. What's the first thing I need to do? Find the quadrant, but before I do that, I need to have sine by itself. So I'm going to have to get rid of that 2. How am I going to get rid of that 2? Divide by 2, yeah. So from here, I'll have sine theta equals 1 over 2. And now we start going into it, it just happens to be the same ratio with the same number. So, I mean, what quadrants are we looking at? Just a second. So, therefore, let's do that first. And in radians, sine what equals 1 over 2? So, in radians, 1 over 6, 1 over 2. And second quad, so going from that, 180 minus 30 is 150. So 150 in radians is 556. So therefore, we have theta equals 556, 556. And I don't need to multiply it this time by 2 at the end, because in the question, it was just theta. It wasn't saying theta over 2 or anything like that. So, anyway, we'll call it there. I've got to just do a few things before roll call starts this morning. So, yeah, if you have any more questions about these, make sure you ask later. yeah, next Tuesday, Albo will be doing some hard questions, probably on some trig function stuff. If I can find anything that we've done towards that point. If not, I'll go back to like hard integration stuff and hard geometrical apps and calculus. So hard chapter 2 and 3 stuff. Alrighty, cool.